One of the first things you need to learn in geology is the definition of rocks and minerals and crystals. And of the three of these, I think crystals is in some way the hardest concept to master. So I want to talk about crystals in this video, obviously in the context of minerals and rocks, but I want to start by focusing on crystals. Now, the very first thing we need to say is that because crystal, the word crystal is a word we use in our regular everyday life, we sort of have to unlearn what we thought a crystal meant. And specifically, what I mean is I do not mean this, okay? I do not mean a beautiful specimen of beautiful facets that has magical healing powers. That's not what a geologist means by a crystal. So what we mean by a crystal is a specific instance or a specific piece of a mineral. And I'll try to explain that in this slideshow. And I'm going to do it through the lens of looking at thin sections. So what is a thin section? A thin section is actually the primary tool used by geologists to study rocks. It consists of a thin slice of rock that's been glued to a glass slide. And when we cut rocks this thin, this is on the order of 30 microns thick. When we cut rocks this thin, for the most part, they're actually transparent. Light can go through them. You can see that on the sample on the left. Most of this is actually transparent. You can actually see it on these four thin sections down here. All of these actually are mostly, for the most part, transparent. And so if we put this in a microscope, light will be able to go through the sample and we'll be able to study the textures and the relationships, the geometric relationships of one mineral or crystal of a mineral to another. The way we do this is through the use of what's called a petrographic or rock microscope. And the idea is, it looks like this. There's a light source down here. So it generates light, and that light then will pass upward through our sample. Our sample is found usually right in here. That's where our thin section goes. And it will pass up, it will be magnified, and then it'll go over to an eyepiece where we can put our eye right here and look at the sample. Now, there's one other thing that happens in a petrographic microscope, and that is before the light passes through our sample, and optionally after the light passes through our sample, the light will be passed through a thin piece of polarizing film. So what does that mean? So here's the light path shown like this. Okay, light's going, in this case, up, but I'm just showing it horizontal here. Here's my light source. Here's my unpolarized regular light. And as it goes through this piece of polarizing film, the result is that the vibrations of the light waves are forced to be either east-west or north-south. So in this case, they're calling them east-west, like this. So they're going up and down like this. We call this now plane polarized light. So the light coming through has been polarized light. The light then will pass through my sample. So here's my thin section right there. And as it passes through crystalline substances, sometimes, actually most of the time, the light will be twisted and distorted. And that distortion happens dependent on the wavelength or the frequency of the light. So certain colors of light will be twisted and distorted more or differently than other frequencies or wavelengths of the light. That light then will pass through a second polarizer. This is called cross-polarized light if it goes through the second polarizer. And the second polarizer is set up right angles to the first. Now, let me back up a second. If I don't do anything to my light, if it comes through the first polarizer and it doesn't go through my sample, or if it goes through my sample without changing, what's going to happen is when that east-west polarized light reaches the north-south, this is now the north-south polarizer, okay? This is north-south. When it hits that polarizer is only going to emit that light that's going north-south, but the light is going only east-west, and so none of the light will go through. So if something doesn't change as the light passes through my sample, the second polarizer will have the effect of completely blocking the light, and everything will turn black. However, if my light changes as it interacts with my mineral, then some of the light and some frequencies of the light will pass through, and I'll be able to see things. The really cool thing here is that due to that distortion of the light, what I'll actually see under cross-polarized light are colors that don't really exist. So let me show you what I mean. So here is a thin section in plain polarized light. These are actually three of them, sorry. Three separate thin sections in plain polarized light. So this is essentially regular light shining up from the bottom through my sample to my eye. And I can see that there are weak colors. There's kind of weak greens and browns maybe here visible, and we'll talk about what all this means. Now, if I insert the second polarizer so that I see cross-polarized light, let me see how to do that here. There it is. This is now cross-polarized light. So the light is going through two polarizers oriented 90 degrees from one another. Now I suddenly see these vibrant, beautiful colors, and these are really gorgeous to look at, okay? The thing I want to remind you is these are not real, right? If you pick up the rock, you're not going to see this. This is only an artifact of the petrographic microscope. Here's another example, actually, in more detail. On the left is the plain polarized light. On the right is the cross-polarized light. We use the cross-polarized light a lot of times because it helps us to identify different kinds of minerals, and often it makes it easier to see the relationship between the crystals of the minerals in the rock. And that's what I want to focus on here. I don't really care that you understand how a petrographic microscope works. I just want you to understand when you look at a slide like the one on the right, you don't think that's what it's going to look at if you just pick up a sample. That's sort of that's an artifact, right? It's not what you would see without a microscope. So here's one final example that's kind of spectacular. On your left is plain polarized light, and I want to start by noticing that you can see a bunch of different forms in this, right? And what I'm going to show you very soon is what you're actually looking at is just one mineral, and you're looking at a bunch of different crystals of that mineral. So each of these crystals in this case has a very elongate shape. Okay, and we'll talk about what that means in a second. But there are multiple crystals of the same mineral in this thin section on the left. Here's what it would look like under cross-polarized light. I think most of you agree that that is a lot cooler, right? That's actually beautiful. Okay, so let's start here. Here is the first sample I want to look at. This is actually a rock that contains just one mineral. The mineral is quartz. Quartz is a super common mineral. Its formula is SiO2. And in this rock, I can actually see multiple crystals of the mineral quartz. For example, there's one crystal here shown in purple, and here's another crystal shown in brown. Now, if I go and look in detail at the structure of the atoms in those crystals, here's what it looks like. So on the left here, this is the crystal structure of quartz. The little red and gray balls correspond to the gray ball is silicon and the red balls are oxygen. And so we can see the crystal structure of quartz. And this structure exists in this orientation all throughout this purple quartz crystal. From over here all the way to the other side. So in theory, if I knew the position of an oxygen ion here, I ought to be able to use this motif or pattern in this orientation to predict the location, the exact location of an oxygen atom way over here, 10 to the 23rd atoms away. So everything within this purple region has exactly the same structure, obviously because it's all quartz, but moreover, that structure in the same orientation. Same thing is true in the brown crystal, but notice that the orientation of the structure has changed, right? This is no longer the same orientation as the quartz crystal above. But the same thing's true. Within this brown crystal, all parts of this crystal have the same structure in this orientation. And that's what we mean by a crystal. So it's an instance or a piece of a mineral. Saying that, it's got to have the same mineral structure in it, but in addition, the orientation of that structure is the same everywhere within the crystal. Here's another example of a rock that's made up of all quartz. So this is again quartz. This is actually a quartz sandstone. And I just want to point out a couple things. We have 3 different crystals of quartz. They're all colored purple now, but they're different crystals of quartz. And the outer limits of the crystal, the boundaries of the crystal, where the crystal ends in this case, they're all rounded, right? And the reason for that is because these crystals of quartz represent sand grains. This is a sandstone. And the way this rock formed, it formed from grains of sand. This is magnified, so these are grains of sand, and they were rounded as they were abraded, as they were being transported in some kind of river. And then they were collected together, and then they were cemented together with more quartz. So everything in here is quartz, but there's one quartz crystal. Here's another quartz crystal, and you can see all the other quartz crystals in here as well. However, it's important to notice When this thing became cemented together, the cement was also quartz. And so everything in here, everything in red here, is yet another crystal of quartz with different orientation, same structure, but a different crystal of quartz. In this particular crystal of quartz, the outer boundaries were not caused by erosion. The outer boundaries are the size of the container in which this crystal of quartz grew. It grew in the interstices between these other sand grains, and so it adopted the shape of its container. And that is one of the things we often find true of crystals, is that the shape of the crystal may be due to different things, but very often crystals have an irregular shape that's due to the fact that they grew within a container of an irregular shape. Here is another rock consisting of just one mineral. In this case, the mineral is calcite and the rock is a limestone. Now, if it looks to you like maybe some of these things represent fossils, you're right, because in this case, the limestone consists of the mineral calcite existing both as fossils. Calcite is the mineral that makes up the fossils, and calcite exists as this very fine-grained cement that's present between the fossils. If we enlarge this thin section, we can just barely see some of the crystals that are in some of the fossils. So if you look carefully, some of these kind of long, thin, skinny things are actually crystals of calcite. But for the most part, the crystals in here are so small that even with a high-powered objective, it's very, very difficult to see the boundaries of the crystals of calcite in this limestone. Here is another rock consisting of all calcite. This is a rock called marble. And in this rock, in fact, all of the crystals are macroscopic. That is to say, they can be seen with the naked eye. So it's pretty easy to see. I think here's one crystal of calcite. And you can see all the crystals here. The boundaries here are very, very clear. And so this will be a rock in which you can see the crystals with the naked eye. But again, nothing really different about what the crystals are. They're instances of the mineral calcite. There's the structure of calcite with slightly different orientations of the structure within each crystal. I want to show you a few more. This is in cross-polarized light. So this is, again, these are artificial colors, but this is kind of what it looks like. And you can kind of see the advantage now. This is a rock. This is actually a granite. And in the granite, there are different minerals and different crystals of those minerals. So in this granite, we have sort of a gray looking mineral. This actually is a feldspar. This is one kind of feldspar called K-spar. Here's another feldspar called plagioclase feldspar. And the brown things in here are a mineral called biotite. Point I want to make is here we have different crystals of different minerals, and the cross-polarized light allows us to see that. One other thing I want to point out in here is that in this particular sample, there are also some opaque minerals. This mineral here, for example, is opaque. And so even in plain polarized light, this would be black. It's a mineral that in fact can't transmit light even in a very, very thin slice. This is actually a mineral called magnetite, which is an iron oxide mineral. Here's another rock in cross-polarized light. So these beautiful colors are not real, but they're cool. So what I want to show you here, this is actually a rock called basalt. And the reason I wanted to show you this is because in this particular case, many of the crystals of different minerals have beautiful shapes. So for example, this one here, I think you can see has a beautiful geometric shape to it. These are beautiful shaped crystals. And here's another one. Look at this beautiful angle here between those, okay? Now, the reason these crystals have beautiful shapes compared to some of the crystals we've seen before is because of how these crystals grew. Everything that's black here, all the black stuff here, represents glass. So you might remember I said that as light passes through the lower polarizer and then the upper polarizer, which is at right angles to it, if nothing happens to that light as it passes through the rock, then the entire light will be blocked. None of it will make it through the second polarizer. And that's what happens with glass. Glass is not a crystalline structure, so that in cross-polarized light, glass looks black. In a rock, glass represents liquid that chilled. So this represents originally liquid. So the history of this rock looks like this. This rock started as liquid with a few crystals in it in a magma chamber, in a pool of magma deep underground. This crystal and the other crystals in here existed. They were growing in the liquid. And when a crystal grows in a liquid, it has no container, right? It can grow as free as it wants. And under those conditions, crystals will often adopt these beautiful crystal boundaries, these very beautiful geometric shapes that you can see in some of these crystals, right? Because there's no container there. They can just grow as free as they want. And then this mixture of liquid and some included crystals was erupted, and the rest of it, the liquid, cooled very, very quickly, so quickly that it transformed to glass. And so the rock now consists of crystals embedded in glass. But the crystals, when they grew, were growing from a liquid, and so they could have these beautiful crystal shapes that are shown in this particular rock. So sometimes crystals will have beautiful shapes, but not always. And when they do, it's because they were able to grow into air or into liquid, something that didn't confine them to a specific shape. A couple other beautiful ones here. In this case, this is a metamorphic rock, and I want to show you it's a mix of microscopic and macroscopic crystals. The microscopic crystals are these very fine-grained crystals of what's called talc. It's a very fine-grained mineral, beautiful mineral here in cross-polarized light. It's got these beautiful pastel colors. The macroscopic, meaning you can see it with the naked eye, crystals are these very large ones I've already outlined in pink here. These are actually a form of garnet. So in this rock, if we were to pick this rock up, we'd notice these great big giant garnets, and then everything else surrounding it would be really fine grained, and we wouldn't be able to see the crystals. But if we had a microscope, we'd see that it is indeed also made up of crystals. Here's another one. This is plain polarized light. I want to show you one of the main reasons we use main reasons we use a microscope is that we can very clearly see the different kinds of minerals in the rock. Here we actually have three different kinds of minerals. There's quartz. That's the kind of light gray. We have this brown here is a mineral called biotite. And in this case, there's a rare but very cool mineral called kyanite. The kyanite crystals in here are really big. This is one big, huge crystal of kyanite. This is one crystal of kyanite. This is definitely macroscopic. You'd be able to see this with the naked eyes, a big blade of kyanite. Super cool. Some of the other crystals, like this little crystal of biotite, would be microscopic. And even though it's hard to see here, there are actually many different crystals of quartz. For example, here's one crystal of quartz. Here's another crystal of quartz. So the quartz actually consists of lots of crystals, most of which are actually microscopic. You wouldn't really be able to pick out those boundaries without the help of a microscope. A couple more here. This is again plain polarized light. I just wanted to point out again, you can see the different kinds of minerals, the different crystals of the different kinds of minerals. Here we actually have four different types of minerals. We have mineral 1, which is clear, mineral 2, which is this green, mineral 3, which is this kind of brown, and mineral 4, which is this opaque mineral there. So one of the reasons we like microscopes is it makes it relatively easy to identify the minerals. And this is kind of a typical rock. It has kind of between 2 to 5 different minerals, many, many crystals of those minerals. Okay, final point I want to make has to do with the size of crystals. Many crystals are visible to the naked eye. For example, I'm going to show you a bunch of crystals of the mineral quartz again. Remember quartz, SiO2. And this is a sandstone made up of it's actually the same sandstone that I showed you before in the thin section, right? Little roundish crystals of quartz that have been cemented together with more quartz. And without a microscope, someone who's young and has good eyes can actually see these quartz crystals without the aid of a microscope. So these are sort of sand-sized crystal grains. Sometimes quartz crystals can grow larger. For example, here are some gigantic crystals of quartz. Each of the specimens in this person's hand is a single crystal of quartz. These are very rare, to be honest, but not as rare as something like this, which is one giant crystal of quartz being held in someone's hand, or even as rare as this, which is an even larger crystal. This is one huge crystal of quartz, okay? Pretty much half as big as a person, right? Or they even get bigger than this. Here's a museum. This thing is actually bigger than that person. This crystal you probably couldn't even carry in a truck. That is one giant crystal of quartz. Obviously, these are exceedingly rare, but they do get that large. For the most part, though, quartz crystals as are most crystals, are small. Most crystals are the size of sand grains shown here or smaller. So here's some magnified, here's a magnified image of those sand grains, and you can see that they're all rounded. These particular sand grains are rounded, but these are all crystals of quartz. This is also a rock consisting of crystals of quartz. This rock is called chert. Once again, it's 100% quartz, but in this case, the quartz is microscopic. In fact, the quartz crystals are so small that even with a petrographic microscope like the one I showed before, you would be unable to see the quartz crystals. The only way to see the quartz crystals in chert would be to use some kind of electron microscope like I've shown here. This is an electron, a scanning electron microscope image of quartz. Just notice that the scale bar here is 10 microns or 10 millionth of an inch long. To put that in perspective, and here by the way, here's a quartz crystal there. Kind of see, here's another one here. These are the quartz crystals that are found in chert, and they are really, really small, on the order of 1 micron. To put that into perspective, 10 microns is about the size of a bacterium, and these guys are almost the size of a virus. They are really, really small. A human hair, the radius of a human hair is shown by this heavy line here. So a human hair would be way, 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 way bigger than these tiny, tiny, tiny quartz crystals in the rock chert. So the point being that crystals can exist from things that are microscopic to things that are the size of a car. They all have exactly the same property though. They are pieces of a mineral with, of course, having a constant mineral structure in them, and that structure is in a single orientation.